Hi y'all, last part for chapter 5 and 6. Sorry, that was loud, I dropped my pen. Okay, so also this one's going to be super short, which is great. And this is the last topic before our next test. So yay. Hopefully you've realized that this test is going to flow much better than the first one. So if you were worried about the first test grade, it's super okay. This one's going to be better, okay? All right, so now we're going to talk about polarity of molecules. And you do have to have a structure drawn, like a Lewis structure, before you can determine polarity. So, for a molecule to be polar, it needs to be unsymmetrical. Okay, and there are two things that will make it polar. Lone pairs on center, or, this is an or situation, different outside atoms. So either one of those will make it polar. There are two exceptions. We'll talk about that in a little bit. But both of these things make it unsymmetrical, even if it looks like in the two dimensions it is symmetrical. So this one has two different atoms. This one is polar molecule. Here we've got no lone pairs, same outside atoms. This one is nonpolar. Okay, remember water really does have these two lone pairs here, and any lone pairs on the center make it polar. So the steps are: draw the structure, determine the geometry. If it has lone pairs, okay, so lone pairs or different outside atoms, that's what makes it polar. If it does not have those, then it's nonpolar. Okay, water will affect solubility of different things because water is special, which we'll talk about more in chapter 11, which is Chem 2. Just know that water is attracted to other water molecules because of their polarity. Because here, I've got this partial positive and this partial negative, so they're going to be attracted to one another. Okay, and there are some molecules that have both polar and nonpolar parts. Soap is one of those. Okay, so is NH3 polar? Again, first, draw it. Don't forget to count your total valence. I've used 6. The other 2 go on nitrogen. So, lone pair, polar. While we're here, let's go ahead and say the shape. Trigonal pyramidal. Less than 109.5. sp3. Okay, it is great to just do it all so you know what's happening. CF4. Dots. Yes, I did skip a step, but I've got 4 plus 7 times 4, which is 28, 32, minus 8, 24. I put those 24 dots around. This is symmetrical completely. There are no outside atoms, no dots on center, so this is nonpolar, which does mean symmetrical. Tetrahedral. (109.5) sp3. Okay, this is the last slide, so I will go back and practice some of these with the other slides we've seen. Okay, so this is chapter 6. Everything else for chapter 6 was hybridization, and then another topic that I deleted, but hybridization I kind of taught with Vesper, and you don't need to know why they hybridize. It's just to make their best shape and their most stable shape, so that's why it happens. So we do need to identify these types of bonds. There may be 1 or 2 questions on this, okay? So make sure you understand. Sigma bonds. Every bond you see has 1 sigma bond. So all single bonds have a sigma bond. All double bonds have a sigma. All triple bonds have 1 sigma. Everything above that 1 sigma bond is a pi bond. Okay, so the first bond will be sigma. Anything else is pi. Also, sigma are going to be stronger than pi bonds. Okay. Pi bonds are going to be perpendicular to the axis. So a sigma bond is when 2 orbitals are connected. They are physically connected with one another, like they're overlapping. A pi bond is if I had, these are my atoms, these are my orbitals. They're just kind of adjacent to each other, and they're attracted that way. They're parallel. Okay? So that is why pi bonds are not as strong, because of that parallelness, when really this one is a sigma bond because they're overlapping. So going back, this molecule has 4 sigma bonds because they're all pi. Or sorry, they're all single, and there are no pi bonds. Going back more, NH3. This one also has 3 sigma, 0 pi, because there's no double bonds. But if we go back even farther into our last video, there are some more. Okay, so I've got 1, 2, 3, 4, 5, 6, 7, 8 single bonds and 1 double. Okay, remember, all bonds have sigma bonds, so there are 9 sigma bonds. And then anything on top of the double, so there's 1 pi bond, because there are 10 bonds total in this drawing. There's probably some more. Where are my structures? Here we go. Well, I want ones with double bonds. Okay, well, let's just draw something larger. Let's say I didn't have one. Okay, this is our structure. So I've got 7 single bonds, 1 double, which equal 8 sigma and 1 pi. So the way this works is sigma, 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 sigma. So one of these is sigma and one of these is pi. Okay, if I had something like this, I've got 3 sigma and 1 pi. So for these bonds, sigma and pi, you do have to count every single bond, not just type of bond. Like a double counts for 2 things. A triple, let me erase these. So let's do something like this. Okay, so that drawing that I just drew, it has 2 sigma, because this one's sigma, sigma, and then these 2 on top are pi. Okay, please let me know if y'all have any questions on that. I'll be happy to give you some worksheets you can practice on with keys if you need them, okay? Just let me know. Y'all have a great day.